Thank you for the introduction, and thanks Jen for inviting me to speak here today. I will stay on the topic of X-ray absorption spectroscopy, but switch to electrochemistry. We'll also see that fast is a relative word. I believe that we measure fast enough to see what we need, but far from 10%. So why do we want to study electrochemistry and electrocatalysis? Well, I mean, electrochemistry can prove very useful and valuable if we want to switch away from our dependence on fossil fuels. We become even more electrified with renewable sources that are intermittent. With these, we can do some very interesting things with electrochemistry. We can, for example, split water to make hydrogen. We can use this in fuel cells later. They're also used in industry. We can reduce CO2, which we don't want too much of CO2, and we can reduce it to useful chemicals, both fuels and other materials. We can also reduce nitrogen to make ammonia, which is which is the fertilizer that feeds the whole planet. And this is a route that would get rid of the thermal catalysis that is nowadays used. And it's very important to point out that electrochemistry takes place at the surfaces. So we really need to study the surfaces if we want to understand the electrochemical reactions that are happening. And why do we want to talk about oxidation and reduction? Well, this is for a platinum 111 model system. So platinum, what you have in your fuel cells. And when you increase the potential from low to high, simulating starting and stopping a fuel cell, you see we have some positive currents here, which is associated to oxidation. And we have some negative currents here associated to the reduction. At least this is what the electrochemists claim. And when they do in situ electrochemical scanning tunneling microscopy, so imaging the surface morphology, we can see how the surface roughens. So starting and stopping your fuel cell by oxidation and reduction, leads to roughening. Also very important electrochemical reactions take place at high potentials where the sample can be oxidized. So for example, the oxygen evolution reaction, which is the bottleneck for green hydrogen production, takes place here at very high potential, way above the oxidation peaks. And this is not only associated to roughening, but also to dissolution. So understanding the oxidation and reduction dynamics is very important. But in order to have a more direct view, except for just measuring the currents, we need to try to do what the surface scientists are doing when they're really looking at the atomic structure and the chemistry of the surface. But this historically has been done in UHV, which is very far from where electrochemistry takes place. So we want to try to make a link between this very detailed surface sensitive information that we could get and a real liquid environment. So we want to measure in situ with surface sensitivity. There is some great advancements that have been made. So people have developed this deep and full ambient pressure X-ray photoelectron spectroscopy technique, where you in your ambient pressure in the vacuum chamber, you can reach high enough pressure so that the liquid water is stable. You can then put your electrodes, dip them, apply potentials, pull up and measure, and you can do this under potential control. But there are struggles with stability, and I would say also to some extent with time dissolution. And you cannot measure at high current densities when bubbles are involved because that would splash into your analysis. So we've decided to use X-ray absorption spectroscopy, which is using hard X-rays instead of soft X-rays, as with XPS. And since the previous speaker already introduced this, I will not go into too much detail. But I want to point out that X-ray absorption spectroscopy is inherently a bulk sensitive technique. You measure either in transmission mode, so the attenuation of the X-ray signal, or the fluorescence yield. And here the probe volume is very large. This is not at all probing the surface of your system. So in order to make this surface sensitive, we have to place some tricks. So we go in with our X-rays and then graze against this geometry for a very nice and flat polished surface. And we go below the critical angle for total external reflection. And then we measure the intensity of the reflected beam as a function of energy. And then we get something that resembles an absorption spectrum, where the signal only orients from the top few nanometers of the surface. And this we did at Balder at Max 4. So we study the the oxidation reduction of a gold model system, because this is one of the simplest and cleanest surfaces that you can start with. And even though it's not platinum what you would use in real application, it's the oxidation and reduction dynamics, it's similar. So this is what the cyclic voltammogram looks like, where you plot the electrochemical current versus the potential. This is a sharp, nice oxidation peak and a sharp reduction peak. And here people claim that, yeah, something happens to the surface, something is oxidized. But we need some direct spectroscopic information or observation to be able to see what is actually happening. And SAINS or X-ray absorption spectroscopy is really good at separating different oxidation states. We have here measured references for metallic gold in red and for gold 3+ oxides and hydroxides. And we see that there's a clear difference. If we then look at our totally reflected X-ray absorption spectra that we measure at low potentials below the oxidation peaks, at high potential above the oxidation peak, we see something that really resembles that of the metallic and oxidized references. So we can measure the oxidation of the surface, and we can be surface sensitive. So now we will show you our time resolved data. This is with 2 seconds per spectra, which for us is very fast. When we tried to do this at DAISY, it took us several minutes, which means that we cannot follow anything in real time. But here we can actually measure while we sweep the potential, as you will see, and we follow the current in the cyclic voltammogram. Here I plot the different SAINS. So basically every SAIN spectra where the time 0 spectra has been subtracted. So we see what happens. So we start increasing the potential, nothing is happening to our spectra. There's some peak here from some contamination, but here comes the oxidation peak, and we see clearly signals in the different SAINS. And when we go into the oxygen evolution reaction, we see that this signal grows even stronger. When we approach the reduction peak in the negative sweep, we see that the signal disappears and we revert back to the metallic surface. And to see this a bit more clearly, we can also plot the area of the different SAINS. So this is just integrating the peak that we see here. Let's see if this movie works. Yeah. So we're off. We're increasing the potential from low to high. Nothing is happening. Here we have the oxidation peak, and we see an increase in the oxide signal. As we go into the oxygen evolution again, we see that it further oxidizes. It stays stable until we reach the reduction peak, and it goes down. And this is very reproducible. This is very stable. We can do another sweep. And we see that when we have the initial oxidation peak, we rapidly form an oxide. It rapidly has a high driving force to oxidize, but then it stabilizes. Until we go into the oxygen evolution reaction, we seem to then further enhance, so cause further oxidation of the surface. I think this is very nice. This is very reproducible. I feel like we can trust and believe in our data and believe in what we see. We can take a closer look at what happens if we then vary the upper potential limit. We see that for all the upper potential limits, we have the very similar behavior at the beginning. We have the formation of this thin oxide. It is slightly growing until a certain point where it starts growing exponentially. And we also see that we can say that the amount of signal is proportional to the oxide thickness. And the thicker the oxide gets, the lower potential you have to go to actually reduce it. This we also see from the shift in the reduction peak in the cyclic voltammogram. If we overlay the data, yeah, we can see that the formation of the oxide nicely correlates with the presence of this oxidation peak in the cyclic voltammogram. When we go to these high current densities in the oxygen evolution reaction, we start to further oxidize and degrade the catalyst, and we need more and more potential to reduce also the thickness. We can also measure this at different scan rates, so we cycle the potential at different speeds. So we have in blue 2 millivolts per second and in red 10 millivolts per second. See, the formation of the thin oxide is not scan rate dependent. It forms very rapidly and the kinetics are so fast that it doesn't depend on how fast we sweep, at least for these rates. But the thick oxide has slower kinetics, and the thickness of that then depends on how much time we actually spend cumulatively at these high potentials. So with that, I would like to quickly summarize. So we have developed this new approach, which allows us to study oxidation and reduction behaviors in real time of single crystal surfaces under potential control. And we've tried to do this, as I said previously, at DAISY, but we could not achieve the time resolution necessary. But yeah, thanks to the stability of the beam at Balder, the focus beam at Balder, and the high flux really made this possible for us. And we can then see that initially the gold 111 is a furic acid forms a very thin surface oxide, just a few nano or a few angstrom thick. Then it grows thicker during the oxygen evolution reaction. And with that, I would like to thank Supervisor Edwin, Andrea, who did most of the work, and of course the Beamline staff and the collaborators in Malmö, you for your attention.